Welcome everyone to this Draco stream where we will hopefully start the implementation of one of the most interesting features of the language. Well, interesting in the specification sense, because this is a feature that we've been missing for many example codes, where it would have been nice instead of long else if chains. And also because we have started specifying things like discriminated unions, where usage is heavily dependent on these, which are match expressions, are equivalent of C# switch statements or switch expressions, and it's essentially something like Kotlin, or more like Rust match expressions, where on the left side you have a pattern or some literal constant, and on the right side you have an expression that optionally yields a value, in the sense that we allow blocks to be on the right side of a match arm, unlike C# switch expressions, for example. So the rough idea is something like you can see in this first snippet that I've written here. Of course, since most things are expressions for us, it's only natural that match expressions can optionally result in some meaningful value, in this case strings. We allow constants on the left side, and in this case we are evaluating the match arms to strings. We have a discard pattern in the form of an underscore, and we optionally allow a guard clause, and just like in Rust, we use the if keyword for that. I don't think that we will need a different keyword for it. As far as I know, C# already had the where keyword, and that's why they, or when, I always mix the two, and that's why they opted for that for switch expressions. And of course, since blocks are expressions as well, this can be used with block constructs on the right side of the match arms, just like you would have big switch case blocks in C#, with the added benefit that you don't need all the breaks and such. And the rough idea is to desugar it into long else if chains for now. We will leave jump table optimization and friends for a later time. For now, it's perfectly fine to just compile each arm into an if else if construct. So for the first case where we match with 0, we just call the equals method on the int32 type and pass in the constant. And since if constructs are also expressions, we simply allow evaluating it to the right side as well. And guard clauses are simply conjugated with the AND operator to the matching arm condition. Now I've put a note here that the discard pattern we will simply compile to true. We can later ideal this with a smarter construct, but for now this will be consistent with the fact that patterns will always emit an expression that does the pattern matching, or the check that the given thing matches the pattern. And for the discard, the simplest is to just yield a true literal. Later we are planning to introduce matching with types, just like in C# match expressions, or C# switch expressions, sorry, or any kind of pattern matching in C# essentially. And we optionally want to allow binding the type to name, or we want to implement flow typing. I am not sure which way we will go, so we won't be bothering with this part today, unfortunately. That will probably be time for another stream. So let's take a look at what we have to do today. Of course, we will have a new keyword, match, and we will also have a new kind of syntax node called a pattern, which is anything that can be on the left side of match expressions. This will be a sort of new family of patterns, just like expressions, statements, or declarations currently, or even type references. And for today, we will only implement literal patterns and the discard or any pattern, if you like. Later, we will add the type pattern with an optional bound name, but again, this probably won't happen today, as we might want to do flow typing. This is undecided, so we will just skip this for now. After we are done with the syntax, we've implemented lexing and parsing for it, and the syntax nodes. We will move on to binding. We will have a bunch of untyped and bound nodes. If anyone has followed the stream previously or is a contributor, knows that we have 2 stages for constructing the AST. First, we transform into an untyped tree where we collect all the constraints for the type system, then we solve them, and with that newfound knowledge, we transform that untyped tree into a bound tree, which is where everything and all types are finally resolved. As for the match construct itself, for all of the arms of the match, we need to check if the given expression can be handled by the pattern on the left. So there's type compatibility. For example, if here I specified a string but num was an int, that would obviously be a type error, so we have to check for that. And we also have to check that the match expression results in some common type that we can resolve to. So for example, if one returns a string and the other one returns a boolean, that's obviously a type error. There's no common type for them unless we decide to default to object, for example. There is also flow analysis. This will very likely happen off stream. We will likely not do flow analysis during the stream because it needs a whole new kind of analysis process for exhaustiveness checking that is very in the planning stages so far, and we have to do some reading on them, some papers, and of course we will have to do lowering to have this feature implemented and to avoid having to write the low-level code generation ourselves. Again, for that we will just desugar the whole thing into a bunch of else if arms for now, and leave the leave the jump table optimization for a bit later. Let me catch up on Twitch chat for a moment. Okay, so Blueberry87 is asking which pattern matching algorithm we are planning to be using. Well, initially we are just going to do a bunch of else if arms, and other than that I honestly have no idea what we are going to go with. We will probably look into what Roslyn is doing, as that has been our main source of inspiration for the whole compiler architecture, and well, most of the things we do there we do because Roslyn did it that way, and it worked out very nicely. So we will first probably look at what Roslyn is doing. As far as I know, they're building some kind of tree and doing bounds checking there. I could be very wrong about this, but we will definitely take a look there, and also read up on some papers that I have saved in some bookmark folder somewhere. Okay, Let's start with the implementation. Let's start writing some code that we gonna want to get working, and what's better than to just paste in this snippet, for example. I already prepared an empty workspace for us. I did what I did last time on stream, which is that I've set up the compiler project to directly execute this workspace that I have here opened, and I've also hacked in all the metadata references so we don't have to invoke the compiler through ms build to get any output. We can just run it directly from Visual Studio. So let's paste this in. Of course, the tools very much won't like this construct, as our language server has no idea about match expressions as of now. And of course num is unknown, but we could just give it 1 for now. And the first error is of course that there's an undefined reference to match, and this is because match is currently interpreted as a name that we want to resolve to some variable or constant, and this is obviously not correct. So first off, let's get rid of this lexing error. Let's introduce match as a new keyword. For that, we will first head into the API part of the compiler, and we will open up token kinds. Here we have a list of keywords here, and they're in alphabetical order, so now I will have to locate where to put match, and I think it should be here. And this is essentially just a huge enum for all the token kinds we have. Apart from that, we will of course have to add this in the lexer as well as a new keyword. The lexer is an internal component, it's not exposed, so it can be found in the internals. And it's very simple to add a new keyword, as we just lex an identifier, and we then just check in this huge block if it matches any of the predefined keywords that we have, and if so, we just override the token kind to be that keyword instead of an identifier. With that, we should have very basic lexing support, but there's one last thing we need to do. Sometimes we want to be able to go from token kind to the keyword string itself, and that can be found in syntax facts, I think. I have no idea where that is. Maybe that one is in the API. Yes. To save space, we don't save the keywords, and then we go from the token kind to keyword instead. So we need to edit here to translate back the match token kind into the keyword match itself. With this, we should have gotten rid of the lexer error. Let's try to run the compiler and see. Okay, we have a bunch of errors, and there's an undefined reference to underscore, but I don't see any for the match keyword anymore. So that one's disappeared. But we can also check by reinstalling the language server, though I don't prefer that because that means I'll have to restart these VS Code instances. So let's commit what we have for now. It's not a lot, but it's honest work, as they say. And this is the lexing part done. Before we can start on the parser itself, we will have to add new kinds of syntax nodes to support the match construct. So let's open up the compiler in VS Code. I usually don't edit the compiler itself in VS Code, but I edit the XMLs that describe the syntax and the bound tree in Visual Studio Code, just because the XML support is better here. I think we should have a file called syntax node, or maybe it's just syntax. Yep. So this is the format that we use to describe our entire syntax tree. We generate it because there's a bunch of CRUD that we generate with it. We generate the syntax factories, visitors, and even syntax rewriters from this description. So what we want to do is introduce a new kind of syntax for match. And now I would put this somewhere below if expressions. So let's just copy the if node, and we will add a match expression syntax instead. So match expression syntax will obviously derive from expression syntaxes, and it's going to be a match expression. Now the documentation comments aren't too helpful for now, but we've added them in the XML, and we decided to keep them around. Now it will start with the match keyword. If someone doesn't know, this syntax tree contains literally every single token, so we're not throwing away anything at the parsing stage. This is to have extra tooling support, easier reformatting and such. We keep all the spacing, the comments, as well as trivia around the tokens, and we keep all the tokens. So the first thing that we stash when parsing match expression is, if you see this sample code, is the match keyword itself, then an open paren, then some kind of expression that contains the value that we want to match. Then it will be a close parenthesis, and then an open brace, then a bunch of match arms, and then a close brace. So this is the match keyword that we're going to store, and we also have a guard built into the mechanism that compiles this syntax tree for us. For tokens, we can specify what kinds of tokens we want to accept here, and this can only be a match token. Now for the parser itself, this is not too useful, but this is very useful when we generate the syntax factory, the factory functions essentially, or writing the formatter. It's very easy to catch bugs, very messed up constructing the parse tree. Now this open parenthesis is actually correct here, but it's before the well, not the condition, but the matched value. Then we have the matched value, not the condition again. I have no idea if this has any special name, so I'll just call it matched value for now. Then we have the close parentheses, that is also correct. This is the reason I kind of chose if expression, because I knew that the prefix was mostly going to be the same. And then we have a field here for called then, which is the then expression for if statements or if expressions. Obviously we won't have that here. We will instead have an open brace, and then a bunch of match arms, and then a close brace. So what I'm going to do is copy this field, and now I'll have to take a look what the open brace is called in the compiler, because I can never remember. Oh, it's called curly. Okay, that makes sense. Do I call it open brace anywhere else? Because I like to be consistent. Yes. Okay, a bunch of places. Okay. And I'll also write the close brace. And here we need to store all the match arms. So let's create a field for that. Since we're already in the match expression, I'm just going to call it arms. Let's call it match arms. Arms in itself sounds weird. And this is going to be a syntax list of something called maybe a match arm syntax is a good name for it. And field itself is missing a bunch of things still. For example, the documentation. And I don't think that we need anything else here. If you're wondering, since we're in XML, the less than and greater than characters cannot be just written like this. This is obviously faulty XML. We have to use these escape sequences, and syntax list is just a special type we have for a list of syntax node. This is because transforming the syntax for us involves more than just a simple projection. We have something called red-green trees, so a syntax list is just a special type that supports everything we need during these transformations, like caching already transformed nodes and such. So we will need a new kind of node for match arms, and the base for that will be just syntax node. That's the kind of the root node of everything. It's defined here. It's a predefined node. We don't define that in XML. Now, the reason that we don't derive from something more specific is because match arm in itself doesn't really make sense in any context. It only makes sense within match expressions, so we don't worry too much about specifying what a match arm really is. It's just syntax. Now, match arms, as we have seen, consist of essentially three main parts: a pattern, an optional guard clause, and the value that they assign the pattern to, essentially. So we will have three main fields, and of course, since we are in the syntax tree, we won't throw away any tokens, so we also store this arrow and the semicolon at the end of the arm. So the first one will be the pattern, and this will be a pattern syntax. Now, pattern syntax is something that does not exist yet. We will have to introduce that in the compiler. After the pattern, there will be an optional guard clause, and I don't think that we have anything like that in the compiler yet, so we're going to create one. And we are just going to create a helper type for that called guard clause syntax. And we are going to make that optional as well. After the optional guard clause and after the pattern, there will be an arrow. And I think we don't have that as a token kind yet. Let's check if we have an arrow. We don't. We only have that on a branch currently, which is about the delegate types. So I'll just leave it to do here. We will add this token later. After the arrow, we have the value of the arm, which is going to be an expression. And finally, there's going to be a semicolon. Now, what I cannot decide if the match arm itself should hold this semicolon, or we should use a separated syntax list here, which allows for trailing, punctuations as well. I'm not sure. For now, what I've mocked up here, it sort of looks like that every arm is terminated by a semicolon. So I think I am going to go with having it in the arm itself. If later we decide against it, we can always just change this to separated syntax list. It's not a huge change. Okay, I think that should be it. And of course we have a bunch of syntax kinds that are not defined yet. Namely the pattern syntax and the guard clause syntax are things that the compiler has no idea about. So let's start with the pattern syntax, because that's going to be just an abstract node. I think that I have the abstract nodes bunched up somewhere, or maybe not. No, it looks like I went in a sort of Fluent style, where below the abstract node I just list all the alternatives, which is no problem. We're just going to start a new abstract node here then, called the pattern syntax, and we're going to base it on syntax node. And for now, we're not going to derive any kind of pattern. For now, we just want to get this tree to compile first. And of course, we have a guard clause syntax that is not defined yet. I'm going to define it right below here since it's needed by the match arm. And it's also just going to be a generic syntax node. And well, currently this is for match arms only. It's just the keyword if and then a condition after. But I'm not going to specify it in the documentation since there's a chance that we are going to reuse this guard clause later on for something else as well. What I'm going to do is actually steal the start of the if expression since it's essentially the same. Let's see. Yes, the keyword if, then an open parenthesis, then the condition itself, and then the close parentheses. So that should be the guard clause. And with that, I think we should be having a compiling tree, and the only correctness thing we are missing is the check for an arrow token, since the arrow token doesn't exist in the compiler yet. Let's see if this compiles. If the XML changes, the source generator is recompiling the tree automatically. Okay, pattern is missing. Can I navigate to see the error? Oh, of course, yeah. So tokens always need a kind, so our mistake is essentially our only thing that we couldn't implement, which was this arrow token kind. So let's quickly fix that. We'll add the token kind for arrows. I have no idea where I'll add it, so for simplicity I'll just shove it at the end. Let's add it to the syntax facts before I forget it, because this is also a token that you can translate back to text very simply. And then let's see the lexer. Now this is a bit harder because I'll always have to find where the minus is. It's here, okay. And if it peaks and equals after it, it's a minus a sign, yep. But if we peak greater than operator after it, then it's going to be an arrow. And with that, we should be having arrow as a token kind. So let's add it here. And with that, we should have the tree compiling, no problem. Yep. Let's commit this. Let's go through what we did. We added the arrow as a token. And we also added the match expression syntax itself with all the details. And we also modeled match arms and guard clauses as well. And we haven't implemented any patterns yet, which is no problem. Let's move on. Let's try to model the two kinds of patterns that we want to implement for today. If we go back to the snippet, we want to have, well, let's go to the snippet that we actually want to get compiling. We have literals, but currently we only have numeric literals, but I think that we can cover all of them with one kind of syntax node. And we have the discard pattern. So let's try to model these. I think we already have a literal expression syntax, so we're going to borrow that and make that into a literal pattern. We're just going to call it a literal pattern syntax. it's going to derive from pattern syntax. And we aren't going to allow every kind of token that we allow in expressions. For example, I don't think we want to match on floats currently. We only care about, well, I would say that we only care about integers for now. We can always expand this list. It's not that hard to do. Strings are a bit more complicated because our strings naturally support interpolation, and they're a bit more complex, so we are not going to deal with them, at least today. We're only going to allow integers for now. And of course we want to model the discard pattern as well. I'm always moving between trying to call it discard or any pattern, since this essentially matches any kind of value. For now we're calling it discard. As far as I know, C# calls it discard as well. And we're only allowing a single kind of token here. And we might also want to have its own token kind for the discard pattern. So underscore could be a special kind of token. I don't think that should be too annoying, since I don't think that one should call anything underscore anyway. So naming your variables underscore or your methods underscore is kind of weird anyway, so I wouldn't mind allocating underscore itself as its own token. So let's do that. Let's allocate a token for that. And just like last time, we're going to, since it technically matches a keyword, I'm going to call it a keyword as well. It might sound weird that we are naming an underscore keyword, but technically it matches the regular expression that we use for keywords and identifiers, so it might not be that bad. Now that should go to D. These here. And let's add this to the lexer. And we also need to add it to syntax facts, because this is again a translatable keyword. And I think we've already specified it in the tree. Yes, it's already specified as a keyword, so let's hope this compiles. Okay, this means that the tree is correct. There's no typos, at least not in the type names. So let's commit this. let's hope that this is all the work we need for the syntax tree. So now we can move on to parsing this construct. I wish I could somehow show you guys both the snippet and the code at the same time, but the idea is that if we find a match keyword, then we're going to expect an open parenthesis, then we will parse an expression, then a close parenthesis, then an open brace, and then a bunch of match arms, and at the end a close brace. And parsing a match arm will consist of parsing a pattern, then an arrow, and then an expression, and finally terminating it with a semicolon. Of course, if after the pattern there's the keyword if, then we parse a guard clause. So let's close everything here, and let's open up the parser, which is a bit more complex. It's still not too bad. Working with a parser is pretty decent. We have a bunch of lookup tables here that we have to maintain whenever we add a new kind of token or syntactic construct. For example, here we have a bunch of token kinds listed for any kind of token that can start an expression. Now, match will happen to be one of those, so we will add it, and it belongs here. Again, this is also alphabetical, so I like to keep it that way. Match is a kind of token that can start an expression, so we add it to that list. And then I'll have to find the place where we start parsing all the expressions that start with a keyword. For example, if expressions. The simplest is to just look for all the instances of the keyword if, and as you can see, it's also in the expression starters here. It's in parse statement. Now the reason is that it's in parse statement is because in statement context, if and all the other control flow things are parsed a bit differently, and the sole reason is that blocks can be expressions and they behave slightly differently in expression and statement context. If you have implemented a language before that does that, you know that there are slight edge cases that you need to account for. So let's add match here as well, as that's a control flow expression. This is parsing a control flow expression. We'll add it here later. And this is parsing a block. Yes, inside block we handle control flow constructs a bit differently again. They're a bit more natural this way. And this is the if expression itself, and this is parsing an atomic expression. This should be the last one, I think, where we need to handle it. Yes, we've gone for full circle. It's added here, so we need to add it here. And we need to write the parser function for it. We will implement that later. First, we will add it to the remaining places, if there's any. Let's quickly recheck. This is parsing the if expression itself. I think that's it. So what we can do is that we navigate to the if expression parser and start implementing this new parser. also going to copy this documentation comment, as I'm very lazy to write it. And we have a bunch of utilities for the parser, so it's pretty easy to write parsing for any construct, well, any decent construct. For example, we know that this parser will only be invoked once we know that the token ahead is the keyword match, so we can just call expect, which will automatically report an error in case it's not actually the match keyword. And then we expect an open parentheses, and I'm just going to copy whatever was in parse if statement, because it's expecting an open parentheses, then it's parsing an expression, and then it's parsing a closed parentheses, just like we need here. The only thing I'm going to do is rename this to matched value. After that, we will need an open brace. And at the end, we will also need a close brace. And between these, we're going to parse a syntax list of match arms. And once this is done, we can construct the syntax node for the match expression. Okay, now let's start worrying about actually parsing those match arms. Now, I think that we can just rely on the fact that the close brace will terminate the whole thing. So what we can do is write something like this dot matches token kind dot close brace, and it will just return that for us here. And here we can just parse an individual match arm. I think we're going to take the control flow context here, since that's going to be significant in the arm value itself. Okay, and here we can just say that we're going to append a new match arm, which is going to be the parsed match arm essentially. And with that, the match expression itself should be covered. Now we just need to implement the arm itself, which is going to be a pattern, an arrow, a value, or rather in more general terms an expression, and then a semicolon. Of course, pattern parsing is not yet implemented. We'll implement that in a bit. We could actually declare it here below all the expression parsing. These are very low level methods. I don't wanna inject it here. Well, this will be good. This is just below string parsing. Visual Studio just crashed a bunch of my processes. Wonderful. Okay, let's continue with parsing a match arm. So after the pattern, there's going to be an optional guard clause. After the guard clause, we always expect an arrow. And finally, we need a value. What's the problem? Oh, parse expression does not. Parse expression does not expect a control flow context, which might mean that we want to get rid of the context parameter. For now I won't, because we might need it eventually. But for parsing the guard clause, we're going to need a new parser. And what I'm going to do is I'm going to just copy the relevant part of parsing an if expression. This should be it. Okay, what are we missing here? Oh, the semicolon. Okay, with regards to the parser, what's the problem here? I know. I think flow analysis has grabbed itself here. Let's try to find a similar construct how we solved it in the parser. Fortunately, the parser is big enough that we can find an example for almost everything as of now. I'll just need to refresh my memory where we needed such things. Well, maybe the simplest is to just search for while loops. Okay, it doesn't look like we have construct quite like this. That's not a problem though. We can make up something. So if anyone doesn't know what the problem here is, we're inverting this match condition, and for some reason C# is not picking up that this close brace is being assigned here. Well, maybe this is just a scope issue. So we could do something like syntax token close brace, and maybe it will like it. Okay, this made the compiler happy, so I'm happy. And the last thing we need is parsing patterns. Now, eventually we want to have more interesting and complex patterns with discriminated unions. We're hoping to start on advanced things like the structuring and matching on types. But for now, we are only interested in two kinds of patterns, literal and discard patterns. So what I'm going to do is just write a very simple temporary parser here that will switch on the current token kind. And on the default, we're just going to do synchronization probably, which is trying to get the parser in a more consistent state. But we'll do that later. In case of integer literals, it's just going to be a literal pattern. I think it's called advance, which takes a single token. Yes. Okay. And in case of token kind dot discard, it's going to be this. So this is very simplistic for now, but it could work. Obviously C# is yelling at me to use a switch expression. We could do that. Oh no, it's the wrong thing. So this is a bit nicer, even though we're going to need to get rid of it. So I want this to be here instead. Let's see if we're actually parsing this code and we get further in compilation. Yes, we are. We actually got to binding, which is transforming the syntax node into the untyped tree, which is the first stage of type checking, essentially. Let's see what this syntax is containing for us. So we're having a bunch of match arms. Let's see. Oh, this is the wrong thing. Let's try to navigate it from this window. I get lost quite easily in the floating window. So we have a bunch of match arms. Let's look at those. It has 4 match arms for us, and I think we have a property to just list out all of them. I think it's going to be here. And here are the match arm syntaxes. And the third one should even have a guard clause. Yes, indeed. And the first one shouldn't have a guard clause. All right, so it looks like that the match parsed successfully. So we're just going to commit it since it's quite a big addition to the parser. This is a fine commit message. I don't really care. We're going to squash it during the PR merge anyway. Okay, I would say let's take 10 minutes, and until then I'll decide if we should move on today with binding, or we should end the stream. Until then, feel free to ask questions. We might cut the stream a bit short since I have packing to do as we're moving offices soon. So if you have questions, drop it in one of the chats that's available, and we will see if we have time for binding today. Unfortunately, binding is usually more complicated, so we might not start on it now. Okay, so no further questions popping up apart from the earlier one about the pattern matching algorithm that we're going to use. So let's quickly recap where we're at. We've essentially done this block. We have added the lexing, parsing, and all the syntax nodes required for supporting a match expression. The next step would be binding, which would be declaring the untied and the bound nodes for the binding process. Then it would be actually writing the transformations to these nodes, which would include the type checking and all the constraints that we need to add on these nodes. This is usually a bit lengthier process, though with the new constraint solver, it's a little bit easier than it was before. And there would be flow analysis, which is a quite difficult process, and we will probably do that off stream. And finally lowering, which would allow us to actually run the code that we have written. Now, unfortunately, this stream has to be a little short. We will end it off here, and we will pick it up next time with binding and hopefully lowering in the new office once we've done moving. So thank you everyone for watching. And if there are questions, you can reach out on Discord, no problem. I'll be happy to answer them. And again, thank you everyone, and have a nice day. Bye bye.